where the nth wave function, the wave function corresponding to the nth eigenvalue, could be written in terms of a Gaussian, the product of a Gaussian, the nth Hermite polynomial, and some coefficient C of n. We had also in the last class derived the generating function for the Hermite polynomials. Now what is left, which allows us to write down any arbitrary Hermite polynomial Hn. What is left is to determine the normalization coefficient C of n. So let us today start off by first determining the normalization coefficient C of n. So in order to do this, what we have to do is we have to ask the question, how much is this integral over here? Because the normalization of the wave function means that we have to take two different wave functions, psi n and psi m. So if psi n is proportional to this and psi m is proportional to this, there are two normalization coefficients which we still have to find. And we ask the question, how much is this integral? This is what we are going to use to determine the normalization coefficient and the relation between the different wave functions. So we want to evaluate this integral, and we proceed to evaluate something which is more general and which is useful in dealing with the wave function for the simple harmonic oscillator. We consider this integral over here. Let us look at this integral a little carefully to make some sense out of it. So the first term in this integral is the generating function for the Hermite polynomials. So if I expand the first term over here in powers of s, I will get s to the power n by n factorial hn xi, sum over all n from 0 to infinity. Then if you look at the second term, this again is the generating function of a Hermite polynomial. So if I expand this, what I get is t to the power m by factorial m hm xi, m going from 0 to infinity. I have this extra term over here, this one more term, e to the power 2 lambda xi minus xi squared, which appears here also. Now e to the power minus xi square appears here too. So we have introduced e to the power minus xi square. The reason why we have 2 lambda xi will become clear as we go on. So it is something extra over here, but the rest of it is quite clear that if you want to evaluate this, you should have all the other terms. So this integral is equal to this integral, and each term over here corresponds to one such integral. Okay, so now we want to evaluate this. Let us do it slowly. So the left hand side, let me show you the left hand side again. So this is what I am calling the left hand side of the expression. So the left hand side can be written in this fashion, where we have e to the power minus xi minus t minus s minus lambda, the whole thing whole squared. So if I expand this, I will get one term which is xi square, which is here. I will get t squared, which is here. I will get s squared, which is here. I will get lambda squared, which is not there, so it has to be, I will get minus lambda squared, so it has to be added. One extra term, lambda square, has to be added. I will get 2s xi, which is there, 2t xi, which is there, 2 lambda xi, which is there. I will get a few extra terms which come from this cross term between t and s, 2ts, which I have to get rid of, so I have this extra term here. I have 2t lambda here and 2s lambda here. Okay, so I have these extra terms which appear in this, which I have to compensate for with this term. So this is equal to the left hand side of the expression which we were evaluating. Now this integral is quite simple to evaluate, because this is nothing but xi plus some constant whole squared, and the range of the integral is from minus infinity to infinity. So the adding of a constant to xi doesn't matter, and we can evaluate. So this is basically e to the power minus xi squared d xi. This is, there is no xi over here, so we can do the xi integral. This is just e to the power minus xi squared d xi, and we know that the integral is root of pi. We have evaluated this a few lectures ago. So this integral over xi gives us square root of pi, and we still have this exponential 2st plus 2s lambda plus 2t lambda plus lambda squared. So the left hand side of the expression we want to evaluate is this, of the equation is this. Now let us look at the right hand side. The right hand side is this sum of from n to 0 to infinity, m to 0 to infinity, s to the power n, t to the power n by factorial n, factorial m, and we have these two Hermite polynomials, and then we have e to the power 2 2 lambda xi and e to the power minus xi squared d xi. Now this e to the power 2 lambda xi, we can expand in powers of lambda and xi, so this gives us the same thing over here, which is a sum over n and a sum over m. In addition, when we expand this, we get one more sum, which is a sum over, let's say, p, some variable p, some index p, and we have lambda to the power of p, 2 to the power of p, because if I expand this, I get lambda to the power of p, 2 to the power of p, and I have xi to the power of p. So this is the expansion of this term over here. So I have also done an expansion of this. So now we have an equality between this and this. What does this allow us to do? What is the purpose of doing all of this? Now, we can use this, so let me keep it here in view. Okay, I have it in the we can use this. So how do we go about using it? So we have this equality that okay, we have an equality which we have derived earlier. Now we can obtain this integral. We can obtain what this integral is. We want to, let's say we want to find out what is the integral of hn xi, hm xi, the product of two different Hermite polynomials of different orders n and m, into xi to the power p e to the power minus xi squared d xi. Suppose we want to evaluate this integral. We can obtain this by equating the coefficients of the corresponding powers of s, that is s to the power of n, t to the power of m, and lambda to the power of p. So if you equate the coefficients of this term on both sides, so the coefficient of s to the power n, t to the power m, lambda to the power p is this integral which we wanted to evaluate on the right hand side. Now you expand this also in these things in s, p, t and lambda. If you do the expansion, then you will get some powers of s, t and lambda. You equate the corresponding powers here and here, and you can use that to find out this integral which we want. So right now we want the integral which we started out to evaluate was this. So if you look at this and compare it with this, we see that we have to look at the case where p is equal to 0 for any general n and m, but p should be equal to 0. We are looking at one particular case where p is 0, which is very simple to deal with. So we have to now look at the expansion of, so we have to consider the term p equal to 0 in the right hand side. So if we look at the term with p equal to 0, then lambda will not appear on the right hand side. The p P equal to 0 means that there is no lambda on the right hand side. Now if I do a series expansion of the left hand side, if that you can think of as two parts. One is a series expansion of this into a series expansion of the rest of it. The series expansion of the rest of it, which is this, will be 1 plus some factors with lambda in it. So this with p equal to 0 is equal to the series expansion of just this term, this e to the power 2 st multiplied by 1. So the left hand side is just the series expansion of e to the root of pi e to the power 2 st for reasons which I just explained, and this is equal to square root of pi sum over n equal to 0 to infinity s to the power n t to the power n 2 to the power n divided by factorial n. Now, so this is the term correspond. So these are all the terms which correspond to p equal to 0 that have no powers of lambda. Now let us look at the right hand side. The right hand side for p equal to 0. So if you look at just the part with p equal to 0, then the right hand side is s to the power n t to the power n by factorial n factorial m, and you have these two Hermite polynomials and you have this. So which is the right hand side written over here. And these two are equal. So if these two are equal, it means that when n and m are different, this integral has to be 0. We only have the terms where n is equal to m. Okay, and when n is equal to m, you can work out what this integral is by just equating these two. Which is what I have written here. So if you evaluate this integral, so what we get is that this integral, the product of the two Hermite polynomials of different order n and m into e to the power minus xi square integrated over d xi is equal to delta nm, which is the Kronecker delta, which means that if n and m are the same, it is 1. If n and m are different, it is 0. And then we have square root of pi into 2 to the power n into factorial n. So this follows by just equating these two. You see that we have a 2 to the power n here. Here we have two powers of factorial n, two factorial n's. Here we have only one. So this goes over there. We have a square root of pi, and we get this equality. So this is the integral which we had set out to evaluate. You please note that we can use the result which we have just derived to obtain the integral with any power of xi over here. You have to just choose p equal to that particular power of xi, and you can use this expression to evaluate the corresponding integral. And this will be useful in doing some of the assignments or some problems which you may encounter in relation to the simple harmonic oscillator. For example, if you are asked to find the expectation value of the position, you will encounter an integral with p equal to 1, because that will have the integral with x. Okay. So coming back to the normalization of the wave function, since we have obtained this relation between the integrals of the Hermite polynomials, we would like to define the wave functions so that they are normalized, which means that if I take two wave functions corresponding to different eigenvalues and multiply them and integrate it over all x, it should be 0, which is what we find these Hermite polynomials satisfy, the condition they satisfy. In addition, we would like that when they are the same, that is, if we take the same wave function and multiply it by its complex conjugate and then integrate over dx, we should get 1. So we want this relation to hold between the wave functions. We want the total integral to be 1 when the two n and m are the same, because this then represents the probability of finding the particle at some position, and the total probability has to be equal to 1. So if we impose this condition that this integral should be 0 when n and m are different, it should be 1 when they are the same, this fixes the normalization of the wave function, it fixes the coefficient Cn, and this is the form of the wave function which we get. Now this extra factor over here, so this is just the square root of this factor here, and this extra factor 1 by this, the square root of square root of m omega by h cross pi, the square root of pi was already there, and this factor over here, square root of m omega by h cross, comes about because this integral here was with respect to d psi, but d psi, the psi over here, psi, is related to x in this way, it is dx by x naught, and this is normalized with respect to x. So we have a 1 by square root of x naught coming in, which is what has gone into this term. Okay, so this is normalized with respect to x, and this is the form for the any arbitrary eigenfunction of the Hamiltonian operator corresponding to an eigenvalue, eigen number n. Okay, so the nth eigenfunction is this, and it is normalized. So we have, let me just summarize what have we achieved till now, what have we obtained. So we have obtained eigenfunctions of the Hamiltonian of the simple harmonic oscillator. We have made these eigenfunctions normalized these eigenfunctions, and we saw that these eigenfunctions are actually orthogonal. I had proved a theorem, if you remember, that the eigenfunctions of a Hermitian operator are orthogonal. The Hamiltonian is a Hermitian operator, and we found that indeed its eigenfunctions are orthogonal, and by suitably choosing the normalization coefficient, we have made them normal also. So now we have a set of orthonormal eigenfunctions. They are all orthogonal to each other. In addition, they are each normalized. So this is what we have till now. Now let us now move on to discussing the time evolution of the wave function. So how do we, let us look at the time evolution of the wave function. What we have been considering till now are the stationary states. So for each of these states which we have, psi n x of t, they are all eigen functions of the Hamiltonian. They correspond to fixed energy levels, and their time evolution is very simple. So let me write down the time evolution of each of these. It is e to the power minus I by h cross e t e n t psi n x. So psi n x are the wave functions which we have been evaluating, we have been finding out till now. We have found these wave functions. These were the time independent part. If you want to look at the time evolution of these wave functions, I had shown earlier that the time evolution of these are called stationary states, and the time evolution of these wave functions is just the change in the phase, and the phase keeps on changing as e to the power minus I by h cross, the energy into time by, that's it, energy by into time. And we also know that the nth energy level is equal to h cross omega n plus half, which allows us to write this as e to the power minus I n plus half omega t psi n x. So for each of these eigenfunctions, this is how it evolves in time, and let us look at how the probability density, which gives us the probability of finding the particle at some position, how this evolves, and this is equal to psi star xt into psi xt. Now this is equal to, so when you take psi star, you get the same factor with a plus sign here. So if you multiply this, then this term exactly cancels out. So this term cancels out between these two, and what you're left with is just, so this is for the particular state n, you're left with psi n x squared. So we see that the probability density does not change in time for these states, and this is quite reasonable, right? This is what we expected, because these are the stationary states, and the expectation values, and nothing changes for these states, nothing changes in time for these states. So this is quite simple. Now suppose we have a situation where the wave function of the particle at the initial instant is not one of these stationary states. So the question now is, suppose I give you some arbitrary psi of, and I want to now look at the time evolution of this. How do we go about doing it? If this were one of the eigenfunctions, it is very simple, right? We have just considered it. Now the question is, suppose I give you a particle in some arbitrary whose wave function is something arbitrary at the initial time t equal to 0. How do we go about looking at this? Okay, so the way we proceed to consider the time evolution of this is as follows. This function can be expanded as a sum of the different eigenfunctions. This is what I had referred to as the eigenfunctions being complete. The eigenfunctions are complete in the sense that you can express any arbitrary wave function in terms of these eigenfunctions. And in this case, we have a discrete set of eigenfunctions enumerated by n, and we can express it in this fashion. Let us look at this a little more closely. So the claim is that any arbitrary wave function can be expressed as n equal to 0 to infinity. These Cn's are some numbers, okay, complex numbers. You should not mistake them for the normalization coefficient capital C of n. Okay, so the claim is that any arbitrary wave function at the initial time t equal to 0 can be expressed as each of these wave functions, each of these eigenfunctions psi n can be written as we saw, Cn Hn into x by x naught into e to the power minus x square by 2 x naught squared, right? This is what we just found, that each of these eigenfunctions can be written as a product of some normalization coefficient, the nth Hermite polynomial, and a Gaussian. What this means is that psi x naught e to the power minus x squared by 2 x naught squared is equal to this sum. E to the power plus. Okay. So let us now ask the question, under what conditions is this kind of a thing valid. Okay, let us see if these wave functions, psi, these eigenfunctions do actually form a complete set of functions or not, complete set of functions or not. Okay, let us actually verify that. Under what conditions can we actually express any arbitrary wave function as a sum of these eigenfunctions? So this is the equivalent to saying that this equality holds. So let us now see under what conditions does this equality does this hold. Now suppose the wave function psi of x 0 at the initial time, suppose the wave function is such that this product over here can be expanded in a Taylor series. Suppose we can expand this function. So let us suppose that this is an analytic function and we can expand it in a Taylor series in powers of x. So suppose we can expand this in some powers of x. So we have bn xn. So we are assuming that this is an analytic function and it can be expanded in a Taylor series like this. Now any x of n can be expressed as a sum of Hermite polynomials. Any x to the power of n can be written as a sum of Hermite polynomials where Hn is the highest such polynomial that will be required, because Hnx will involve x to the power n, and by using appropriate lower Hermite polynomials I can get rid of all the other lower powers of x so that only x to the power n remains. So x to the power n can be expressed as a sum of Hermite polynomials at most involving Hn and lower values of n. Okay. So if this function can be expressed in a Taylor series in powers of x, it can also be expressed in terms of Hermite polynomials, because each x to the power n can be expressed in terms of Hermite polynomials. Okay, so this equality holds as long as this function is analytic. Actually, this equality I can express it even for a more general class of functions, but here we have shown that it at least holds if this function is analytic. Okay. So if this function can be expanded in a Taylor series, then I can express it as a sum of, then I can express this as a sum of Hermite polynomials, and this is the kind of wave functions we are going to deal with in this over here. So all the wave functions we are going to deal with can actually do actually satisfy this condition. So it is a valid assumption that we can express any wave function as a sum of the eigenfunctions for this case, in this case. And this is true in general, not only for the simple harmonic oscillator, but for any problem in quantum mechanics, this holds. So we see that the eigenfunctions of the simple harmonic oscillator are indeed a complete set of functions, and we can express any function with this kind of a caveat that the function itself can be expanded in a Taylor series. So we can express any function as a sum of these eigenfunctions. So suppose we do express psi x at the initial time in terms of the eigenfunctions, then the time evolution is very easy, because we know that psi x naught is equal to n equal to 0 to infinity Cn psi n x, and we know how each of these ones evolve in time, and we can use this to find out how the left hand side, this wave function, evolves in time. So what does this give us? This gives us the fact that psi x t is equal to so psi x t is equal to n going from 0 to infinity Cn e to the power, here I have minus I n plus half omega t psi n x 0. So if I can express the wave function at the initial instant in terms of these eigenfunctions with these coefficients c of n, the time evolution is very simple to find out, because we know how each of these evolves. It evolves in this fashion, and the total wave function, the time evolution of the total wave function can be found by just adding up these wave functions at some later time with the same coefficients. Okay. We also need to know how to obtain the coefficients c of n given the wave function psi, given the initial wave function. So that is also pretty simple, because let us do that. So c of n is equal to psi star n x psi x dx. Let us just check this. This is equal to Cn x, and this I can expand and this integral is 0 if n and m are different. It is only 1, it is equal to 1 when n and m are the same. So it gives us Cn, when m is not equal to n, this integral disappears. So we see that Cn can be obtained in this fashion. So the problem of the time evolution is very simple. All you have to do is you have to express the initial wave function in terms of the eigenfunctions, and these coefficients of this expansion can be easily found in this fashion. Once you know the coefficients of expansion, you can just write it like this, and then you can evaluate the same wave function at some later time in this fashion. So it is quite simple. There is no problem at all. In addition, if the wave function is normalized, so if initially psi x is normalized, which is this condition, this implies that the sum of the mod of Cn squared is equal to 1. If this is equal to 1, then it implies that the sum of these coefficients of expansion is equal to 1. These are all things which I had told you in the general situation without reference to a particular problem. I had told you these things earlier. Now we are actually encountering them again with reference to the simple harmonic oscillator problem. Okay. You could also ask, how does the expectation value of some quantity evolve in time? So let us also look at that. We could also ask the question, for example, how does the expectation value of x evolve in time for a given wave function? So the question we will address next is, how does the expectation value of some, could be anything, but let us look at x to start with. How does this evolve in time? So this, for an arbitrary wave function, for the simple harmonic oscillator. So this is equal to psi x t star into psi x t into x dx. Right, this is what is the expectation value of x. And the question is, how does this change in time? Now, this psi of x and psi star of x and t, we know how that it evolves in time. So this is equal to integral, and then we have a sum n going from 0 to infinity. So let us first expand psi star xt. So psi star xt will be Cn star And then we have the time evolution part, which is now e to the power I n plus half omega t. Because we have a complex conjugate, the minus sign has gone. And then we have psi nx. Let us expand psi x, so let us write it here, this into let us expand psi x, so we will use m is equal to 0 to infinity Cm e to the power I m plus half omega t, minus sign here, and here we have these wave functions are real, so the complex the eigenfunctions psi n are real, so the star doesn't matter. And then we have psi mx into x into dx. This is just the multiplication sign. Okay, this is not, I'll get rid of it. So we have this big integral. Let us simplify this a little bit. So this becomes equal to, let us take out the factors which don't involve x. So they can be taken outside the integral. So we have two sums outside the integral, sum over n, sum over m. I will not write in the range, it all goes from 0 to infinity, and the integral is from minus infinity to infinity. So I have this sum outside, and then I have Cm star into Cn, and then I have, if you consider these two terms, what we have left is e to the power I m minus n omega t, because these factors of half cancel out. And then we have an integral, so let me write down the integral here. So the integral is psi mx psi n x x dx.
n minus n Cm star is I plus
Right, so this is correct. Okay, this is correct, because Cm star, so m will have a positive sign and n will have the negative sign. I might have interchanged m and n between this and this, that doesn't matter, because they are just dummy indices. Okay, so this is the quantity, this is how the expectation value of x evolves in time. Now let us look at this quantity over here. This quantity over here, for any particular, so let us look at this quantity. So the quantity which is of interest now is psi mx psi n x into x dx. This is a number. So suppose I fix m, I fix n, then this is nothing but a number, right? This is one integral. And this integral, this number, so I have a set, so for different values of m and n, I have different numbers. Okay, and this set of numbers, so these numbers I can represent in this fashion. So let me put it like this. I'm going to show the m index in this direction, and I'm going to show the n in this direction. So this I can call, and I have some numbers now. So the first number could be correspond to m equal to 0, n equal to 0. These numbers run from 0 to 1. So I have m going from 0, 1, 2, 3, 4, etc. n going from 0, 1, 2, 3, 4, etc. Okay. So if I fix m, I fix n, I do the integral. So this is one function, this is a different function, and I put in x here, I do this integral. The way to do the integral, evaluate the integral, is to use those relations which we did in the beginning of today's class. So we have to use these, you have to use this equality, we have to equate this to this. Look at the appropriate power of p, lambda, appropriate value of p. So we have to equate these for the appropriate value of p to get p equal to 1 in this case, and then the appropriate value of n and m to find out what this integral is going to be. But it can be done, not very difficult. I will not do it here, and I will leave it for you to do as an exercise. Okay, but it can be done, and suppose we do it, then we will get a number. So we can change m and n and repeat the integral. We will get different number for different values of m and n. And these numbers, so let us call this x00, 0, x, then we have 0, 1, x0, 2, and here we have x 1, 0, because I'm showing the, sorry, this will be, yeah, value of n and then the value of m. Okay, column and row. Or you could use row, column, whichever. Okay, doesn't that is a matter of convention. So we can fix the convention. Okay. So this will be a set of numbers, and this set of numbers we can represent in the form of a matrix. So this will be x 2, 0, and here I have x 1, 1, x 1, 2, etc. So there will be a whole set of numbers, and these numbers are what is called the matrix representation of the particular operator or of the particular quantity. So this is called matrix representation. Let me write it here. Representation. So this is finally a matrix, and we can denote this matrix as x n m. Okay, we can put brackets here also. Let us put brackets here to denote that it is the okay, so we will have this. So basically what I have told you is that this integral over here is a matrix x n m. Okay, and the time evolution of the expectation value of x is equal to sum over n, n and m, then I have c m star c n e to the power I m minus n omega t, and then I have the matrix n m. Okay. You can similarly work out the matrix representation of any other operator. For example, we can work out the matrix representation of the operator P. So what is the matrix representation of the operator P? So this is actually the matrix representation of the operator X. So the matrix representation of the operator P, this will be equal to, in this case, psi n x, P acting on psi mx dx, and this will be a infinite dimensional matrix, because n and m can take all set of values from 0 to infinity. Okay, so the expectation value of any quantity, any physical quantity, the position, the momentum, or functions of these can be expressed in terms of these matrix elements and a sum over these time dependent parts. Okay. So today I will not go on to something new. Let me just finish here. Tomorrow we shall consider one example of this, one example where we shall look at the time evolution of a particular wave function and also some of the expectation values. I will not deal with the matrix representations of operators anymore right now, but we shall come back to it later, and I shall leave evaluating these matrices, the matrix elements corresponding to say the operator x or the operator p, in exercises. So I shall give you exercises where these will be given. You will be asked to evaluate these quantities. Okay, so for today I will stop here.